In the last lesson, we looked at what the concept of combinations is. It's a way of counting things where order doesn't matter. At least that's one way of expressing it. In this lesson, we are going to tie a few things together. So we're going to look at something called Pascal's triangle. We're also going to look at something called the binomial expansion. And we're going to see how we can relate that to combinations as well. So let's just jump right in and start with Pascal's triangle. So the triangle shown below is known as Pascal's triangle, and it's a pattern. It was formalized by a French mathematician. As you can see, he lived he was born about 400 years ago, so it's been around for a while, this idea. And the idea behind the triangle is we form new rows, new items in the triangle using this pattern here. If I take two numbers, say I just take these two numbers, and add them together, 1 plus 2, we get the number that we place between it and below it. So 1 plus 2 equals 3. And that works for any number on the triangle once we got started. Obviously, there's no numbers above this number from which I can add. There's also no two numbers that I can add together to get either one of these ones. So the first three numbers, the first two rows, are given. But from there on out, then the triangle forms itself. So if I add 1 plus 1 together, I get the 2 that's between it. And as far as the numbers on the outside go, they're always going to be 1, because we can assume that we're adding this 1, well, to nothing. There's nothing to the left of it. I mean, nothing to the left. We can think of it like it's a 0. Don't need to draw it in, but it's just that one number. So if it's 1 and, if it's always going to be 1, then we're just going to be adding 0 to 1 over and over. So the outside row is always 1. So let's do the next few rows, fill this in. So if the outside row is always going to be 1, I'm going to do this nice and neat. I'm going to give myself a line to work on. So let's see. I'll erase this afterwards. But if the outside number is always 1, okay, there's a 1 there, and 1 plus 3 equals 4, right? So that's going to give me a 4 in between them. 3 plus 3 is going to equal 6. And then 3 plus 1 is going to equal 4 again. And then I'll have 1 on the outside row one more time. And then get rid of this line, and, fairly neat. One thing you might notice, it's fairly symmetrical, right? Or it's actually very symmetrical. If I were to draw a line down the middle, like this, well, that 6 should be a bit farther over, I guess, but the numbers on either side of the line are mirror images of each other. I don't mean that they're exact mirror images, so I'm writing my 4s or my 3s backwards, but we got the same numbers on both sides of that vertical line. Now that I've seen the 6 isn't centered, it's bothering me. There we go. All right, let's do the next row. So we're going to have a 1, 5, 10, 10, 5, 1. Again, symmetrical, right? And then the 6th row is going to be 1, 6, 15, 20, 15, 6, and 1. All right. Now, there's a couple special things that we need to make note of. The top row, we actually call the 0th row. And we'll see why later. It comes in handy for certain mathematical concepts. So we're going to call the first row actually the 0th row. So I won't call it the first row anymore. I'll call it the top row maybe, but the top row is the 0th row. And then the next row down is actually the first row, and so on. Another thing that we can then see is there's always, like in the 0th row, there's one term. In the first row, there's 2 terms. In the second row, there's 3 terms, and so on. So if I just randomly pick a row, like the 5th row, if we count up, we'll see 1, 2, 3, 4, 5, 6 terms in the 5th row. So there's always one more term in a row than the row number. That means that we can number terms as well. So if I were to number the terms in a row, let's do this in a different color. So if I say term number, then this would be the 0th term, and the first term, and the second term, and the third, and the fourth, and the fifth, and the sixth. So again, the 6th row, as we saw, is going to have 7 terms in it, but we don't number them 1, 2, 3, 4, 5, 6, 7. We number them 0, 1, 2, 3, 4, 5, 6. And again, that's for a very specific mathematical reason, which we'll see in just a moment. One of the things that we can see, well, if I look at the key ideas, I've already talked about some of them. The first element in any row is considered the 0th element, right? So the 0th element in every one of these rows here is 1. So the 0th element is always going to equal 1. So that's an interesting thing to keep in mind. Oops, didn't mean to do that. So it always is equal to 1. For any row, the number of elements is always 1 more than the row number. So the nth row will have n plus 1 elements. So we've talked about that. Pascal's method to determine any value, determine the sum of the two values diagonally above it. Already talked about that. And so this is Pascal's method here. Determine any value. So a little word about the terminology here. This Tn minus r. If we're letting n represent the row number and r represent the term number, okay? So I need to include that. So where n is the row number and r is the term number. Sorry for the sloppy writing. I'd fix it, but then I'd have to spend more time, and you get the idea. So what does that mean? Say I picked, if I wanted to, let's say, find out, well, the next row down. Say I wanted to find out what was in here. I know I've got these things are getting messy with it. I've put the term numbers there and so on. But say I wanted to find out the next term. So I know 20 plus 15 gives me 35, right? I'm going to erase this so as to not keep it messy looking. But 20 plus 15 equals 35. That would give me a term in the 7th row. And that term would be the 1, 2, 3, 4. It would actually be the 5th term in the 7th row. Sorry, actually the 0. Let me start at 0 on the left. Actually, you know what? I'm going to I know I just did this. I'm going to backtrack to some that where I can actually see it a bit better. Let's go to this one up here instead. 5 and 10, that combines to give 15. All right, so that's in the 5th row, so that's my n. And this 15 is the second term, if we start counting at 0, so that my r would be 2. So this term here, this 15 here, it would be in the 6th row. It would be T6, comma 2 for the second term. That's what this terminology is talking about. So that 5 that I've got circled up above, that's in the 5th row. And it's the first term, right? Because we start at 0. The 1 would be 0, the 5 would be 1, plus the term beside it, which would be the 5th row again. And then the term beside it is the second term, so that's r plus 1. And that's going to equal, adding 1 to the row would be the 6th row, and then that's going to be the second term as well. So compare that to the formula just above highlighted in green, and you'll see, and with this example that I just did where I circled those green numbers, you should see what I'm talking about. All right, what else do we know? So we can actually figure out a formula for the sum of each row. Well, actually, let's start by just writing down the numbers. So the sum, if we add up all the numbers in the 0th row, it's 1. And in the first row, it's 2. And then in, the second row, 1 plus 2 plus 1 equals 4. And then 1 plus 3 plus 3 plus 1 equals 8. And so on. Then I get 16. I'm going to erase this now. And this, and this, and that. And that, and that. Good job. All right, the next row down, although I went a little too far, I guess, didn't I? This was a 5, this was a 10. The next row, 1 plus 5 plus 10 plus 10 plus 5 plus 1 equals 32, and then 64. Notice how each row is double the row before it. 1, 2, 4, 8, 16, 32. We've seen this idea before when you're talking about the number of elements in a set. We can write it in an exponential form. I can think of, if I have a base 2, if it's doubling every time, let's think of a base 2. 2 to the 1 equals 2. 2 to the 2 equals 4. 2 to the 3 equals 8, and so on. And what about this 1, 2, 3, 4 exponents? Well, look, that happens to match up with the row numbers, so that's convenient. So we know that the 5th row will have a sum of 2 to the 5. We know the 6th row will have a sum of 2 to the 6. We know that the 100th row, if I was interested in it, would have a sum of 2 to the 100. Even the 0th row, because anything to the exponent 0 equals 1, so that makes sense. Now we have one other thing that we can now tie Pascal's triangle together with combinations, and that is if we were to take the row number. Remember, we've seen these numbers n and r before, so n is the row number, and r is the term number. Then, well, if I wanted to find a combination, if I wanted to know without having Pascal's triangle, what that top element was, it's in the 0th row, and it's the 0th term, so I should be able to write it as 0, C, 0. And my calculator, oops, I didn't want to go to my Desmos grapher, I wanted to go to the Desmos calculator and show you that 0, choose 0. Oh, I forgot. I have to type it in differently on this calculator, don't I? Backspace, backspace. So I do my function first, NCR, and then I go 0, 0 on this calculator. 0, 0. And over on the right, where it says your answer shows up on this side, yes, I got 1. That's what I was expecting, right? Because 0, choose 0. This should equal this 1 over on the left. And then the next row down, well, it's the first row, 0th term. And then I've got the first row, term 1. Those should also equal 1, right? This one should equal this one on the left. This one in purple should equal this one in purple on the left. So let's do 1, choose 0 and 1, choose 1 and see if we get the same thing. 1, 0. Yes, that equals 1. 1, 1. Yep, that also equals 1. So it seems to be working. Let's try a couple more. All right, so the next row down should be 2, choose 0, 2, choose 1, and 2, choose 2. That would be these elements respectively that I'm circling, matching up the colors. So I should get 1, 2, 1 if I do 2, choose 0, 2, choose 1, and 2, choose 2. That's C. First one was 2, choose 0. and that equals 1. And that should make sense, right? Because combinations, how many ways can I arrange, or how many ways can I choose 0 elements out of 2 options? There's only one way to take nothing. But how many ways can I take 1 element out of 2 items? Logic tells us it should be 2, and so does combinations. How many ways can I take 2 elements from 2 options if order doesn't matter? Well, it's back to 1. So again, yeah, it matched up. So over and over, what we're going to see is I can get any element in any row just by doing combinations. That's really helpful. The reason why that's really helpful, let me just write it out for row 3. The reason why that's really helpful is because you may have already noticed a drawback in drawing out Pascal's triangle this way. The drawback is that, say I wanted to know what elements were in the 50th row, that would mean I'd have to do the 0 through 49th row before it to then get to the elements in the 50th row. But combinations don't require me to do this. I could jump down to any row I want without having to do the ones before it. So if I wanted to do the 6th row, let's do the first few elements of the 6th row, just to confirm. And actually, let's do a couple middle elements of the 6th row. No, let's do the, sorry, just changing my mind all over the place. Let's do the first 4 elements of the 6th row. 6, choose 0. 6, choose 1. 6, choose 2. And 6, choose 3. Those are the first 4 elements of the 6th row. So this one, green, purple, and baby blue. So we should get 1, 6, 15, and 20 by doing 6, choose 0, 6, choose 1, 6, choose 2, and 6, choose 3. Well, I got 1 for the first one. That worked. I think I was supposed to get 6 for the next one, wasn't I? And I did. Now I forget what I was supposed to get for the next one, but that's okay, because combinations will tell me 6, choose 2 was equal to 15. Did that match? I think it does. Yep, the third one over was 15. And I should get a 20 for the next one. 6, nope. NCR, 6, choose 3. And that equals 20. Beautiful. Okay, so it's all working out exactly the way we would expect it to. So that's Pascal's triangle. Specifically, what we're interested in, though, well, we're interested in both. Sometimes we're going to want to draw it out using just the numbers, but sometimes we're definitely going to want to use combinations. So the next idea, there's certain applications that we can use for Pascal's triangle force. So such as analyzing the number of roots. So if you think of a checkerboard getting from one side of the board to the other, then there's a certain number of ways it can go. So checkers can only move diagonally forward. So if a checker's here, it could move, if it's here, then it can move here or here. And then if it's here, then it could move here or here. If it's here, then it could move here or here, and so on. It can only move diagonally, right? There's really 2 options. From any given space, a checker only has 2 options of places it can go. So that's how checkers move. If we could use Pascal's triangle, though, to help us count up the number of ways to get to a particular space. So if we're starting at where it shows, let's put a 1 there, like the 0th row of Pascal's triangle. There's one way that it can get from where it starts to that space there. There's also one way to get to that space there. That's the only, there's one way to each of those places. So that's how we think about it. We want to get to those squares, one way to each of them. It is possible to get to this square here, and there's only one way to do it. We have to go through this square first, right? And there's only one way to get to this one on the right that I just filled the number in. We have to go through this square first. But to get to this square, there's actually two ways to get to it. We could go this way, or we could go this way. So that's the two paths to get to that square. There's one way to get to this square. There's one way to get to this outside square here. But Pascal's triangle tells me there's three ways to get to this square. Well, let's see. We could go this way. We could go this way. Or we could go this way. So it turns out that Pascal's triangle is right. There were three ways to get to that square. And there's going to be three ways to get to this square. So I don't need to think about the actual paths in each case. I can just add things up. However, you'll notice that the board runs out here on the left. So that I can't get to over here off the board because I'm not allowed to go there. But there's still four ways to get here, and six ways to get to this one, and four. And I can go to this square, so there's one way to get to that. Now this square here, how many ways are there to get to it? Well, again, it's always adding the two that are above it, but there's can't be here, so really there's four ways to get to this one as well. So I can keep using Pascal to figure out that there's four ways to get to this square. And then 10, and 10, and 5. So the numbers, it's not, up till now, it had been pretty much an exact Pascal's triangle. But now we can see that it starts to change a little bit based on circumstances. We still keep using Pascal's method, though. So 10 plus 4 is 14, 20, 15. And this square here on the right, there's only one way to get to it, and that's by going through this square first. So if there's 5 ways to get to that square, there's 5 ways to get to this square as well. And then there's 14, 34, 35, and 20. So I've run out of places. This was this is where I wanted to get to, right? To become a king, which is what this question was asking us to do, we have to somehow get from one side of the board to the other. It turns out that there's 14 roots to get to one square, 34 roots to get to another square, 35 roots to get to that middle-ish square, and 20 roots to get to that other square on the end. Every one of those is a different root, and so for the total number of roots, overall, we would add them all up. 14 plus 34 is 48, plus 35 is 83, plus 20 is 103. There's actually 103 roots that little checker could take to become a king. This is one where we do want to use Pascal's triangle to help us figure it out, because it allows us to see where, especially with the board being cut off on the sides, it allows us to see exactly what happened beforehand. In other words, we don't have the nice Pascal's triangle, the perfect triangle, like I can do with combinations, because this one's chopped off. It doesn't have the one here and then the one that we'd have over here and so on. It's not a perfect Pascal's triangle, so the combinations isn't as helpful to us in that case. Oh, before I move on, I just want to quickly, I haven't talked about this version of Pascal's method, but hopefully if you understood what I did in green, highlighted in green over on the left, you'll understand that NCR plus NCR plus 1 equals N plus 1 CR plus 1 is really, again, just showing us how we can take two side-by-side elements in the table, and then we get an element that's between them in the row below. So check that out. So again, you can compare that to, say, pick any two elements. Say I pick these two elements. So if N was 2, then and R was 1, then NCR is the first one on the left. NCR plus 1 would be the 2C2, and N plus 1 would give me a row 3. R1 plus 1 would give me the element 2. So there's another version of Pascal's method. Traveling through a grid of streets. Only moving south or east. So if we start at the top, we're only allowed to, if we start up here, and we're only allowed to go downwards or to the right, how many ways, how many paths are there to get to the bottom right? So we want to get down to here as our destination, and we're going to have different restrictions put upon us as we do it. So there's a couple ways that we can think about it. There's only one. Let's use the combinations way first, because that's easier. So we want to get to this square down at the bottom, that circle. We have 1, 2, 3, 4, 5 blocks down that we have to travel. Let's think of that as 5 rows. And we have, let's use a different color. One, 2, 3, 4, 5, 6, 7 columns to the right that we have to travel. And we can call them blocks if we want to, because that's what the question was talking about. So imagine, again, this is supposed to be a grid. Let's imagine we're in some blocked out type city like New York, where everything's nice and square for the most part. And we've got these grids, this block. So we want to start where the asterisk is in the top left, and we want to end up where the circle is at the bottom right. If I have to go down 5 blocks one way or another, and 7 blocks to the right, to the east, then we have to cover 12 blocks. Now, there's all kinds of different ways we could go, right? I could go, I don't know, like this is one possible way, but it's certainly not the only way. I could go like this, or I could go all the way over like this. So there's many different ways, as we're going to see. There's 12 blocks altogether. We just want to get to that cell with the circle around it. So if there's 12 blocks, then we could do, using combinations, we could do 12, choose 5. So in other words, 5 ways to get down to the bottom row. Or we could do 12, choose 7. Because remember Pascal's triangle, these are just cells within Pascal's triangle. Remember, it's symmetrical. 12, choose 5. There's going to be 13 elements in the 12th row of Pascal's triangle. So that 6th one's going to be right in the middle of that 13th. The 5th one and the 7th one are going to be exactly the same because of that symmetry of Pascal's triangle. And we'll be able to see how many different rows or how many different paths there are to take. So let's try 12, choose 5 on our calculator. Oops, I did not clear that away. Okay, let's get rid of some stuff. Try again. 12, choose 5. 792. Okay, well, let's try 12, choose 7, just to show that it should be the same thing. Lo and behold, it is. So either way we do it, there's 792. So Pascal's triangle allowed me to figure that out. If I wanted to draw it out, I'll just do it quickly. I'll try to do it quickly so you can compare. But imagine turning your head, tilting it to the left, so that this asterisk is at the top of Pascal's triangle. Then we had a 1 and a 1 below it. And then we had a 1, 2, 1. So again, you have to tilt your head to the left or else turn your paper if you've got paper in front of you. If I follow Pascal's triangle, then I'm going to get a bunch of rows. Let me just stop talking so I can focus on doing this quickly. But you follow along. Once I get here, remember, I can't go off the screen, so then things get a bit funny. I can still get a 6 here, though. Sorry, brain fart, 56. Uh, 34, 84, 36. Sometimes it helps me to say it out loud. 252. 210, 90, 120, 462, 330, 330, I get 792. Does that number sound familiar? Whoop, there we go, same number. So again, using Pascal's method, or using combinations actually, rather than, is a lot quicker than just having to fill in all the numbers for Pascal's triangle. So I wanted to show you that so that we could, so you have something to compare it to. All right. But now I'm going to erase it. All my hard work. What a shame. Because I want to use this grid again for something else. All right, from the top left to the bottom right going through point B. So now we have to make a pit stop here at B. Well, if we do that, here's how we could do it using Pascal's method again. Let's start with just drawing it. 1, 1, 1, 3, 1, oops. But actually, there's no point in putting this 1 down here. Let me just, this 1, there's no point in, interesting. There's no point in putting that 1 there because I can't get back to B from there. I'm not allowed to move back up. So that was a mistake to fill that in. So there's actually 4 ways to get from where I started. Let's call that A since there's a B and a C, and we say that D is where we're trying to end up. So there's 4 ways to get from A to B. Did I get that right? No. How did I get a 3 there? Confused me. I know what I did. I was still thinking Pascal's triangle. So this is a 1. This should have just been a 2, and this should have been a 3. That's better. I knew something didn't seem right. There's 3 ways to get from A to B. If I have to go through B, that means I have to start off from B again. There's 3 ways to get to this element and 3 ways to get to this element, because I can't have numbers up here, can I? Because they wouldn't go through B. So I have to start out at B for my next part, but then I can carry on. Then I'd have 3 and 6 and 3, and then I can't go any lower because then I wouldn't be able to get back to C. So I'd have 9 and 9 and 3 over here. I'd have 18 and 12, and then I'd have 30 ways to get from A to C. And then from C, I could go to D by going 30, 30, 30, 60, 30, and 90, 90, and finally at D, I'd have 180. Okay, so we got 180. So this time I started just by counting first, and I got 180. But I could use combinations for this as well. So again, I need to go... Oh, my bad. That was for part C. Oh my goodness, so many mistakes today. I mean, not big mistakes, but just doing things wrong. What I just answered was part C. I'm going to have to come back for part B. So there's my answer for part C. Let me backtrack and do part B now. Again, that shouldn't take long. I'm just not doing it in the right order. So if I had to go through B, okay, I didn't have to erase all of that, I suppose. But I can't erase just, let's see. All right. So I can erase this part. Let's keep some of it. Okay, let's keep that at least. 6, but I can still go, I don't have to go through C, so I can just keep going down. 9, 9, 3, 12, 18, 12, 3, 15, 30, 30, 15, 3, 45, 60, 45, 18, 105, 105, 63, 210, 168, and 378. So that's how many ways there were to do part B. 378. That goes there. All right. But as I started to say, we could use combinations to actually do that as well. So first I want to go from A to B. So to go from A to B, I have to cover 3 blocks. I have to go down by 1 block and 2 blocks to the right, however I do it. So I could do 3, choose 1, or 3, choose 2. We've seen before that it doesn't matter. And then from B to D, I have to go 1, 2, 3, 4, 5 blocks to the right and down by 4 blocks. So I have to cover 9 more blocks, and I could do 9, choose 5, or 9, choose 4, because we've seen it doesn't matter if I count rows or columns. Same thing is going to work out. So, and we're going to multiply them together because it's an and. First I have to go through B, and I then have to get to D. So back to the fundamental counting principle. So the way I'd show this one is I would do 3, choose 1, and then I'd multiply that times 9, choose 5, or 9, choose 4, as I already said. Doesn't matter which. So multiplying them together, 378. That down there in the bottom right, before I get rid of it too quickly. Yeah, 378. That might seem familiar because that's what I got using just the counting of the boxes. So this last one, where I have to go through B and C before I get to D, I could still do 3, choose 1. And then to get from B to C, I have to go right by 3 and down by 2. So there's 5 total blocks, and I'll just do 5, choose 2. And then to get from C to D, I have 4 blocks to cover, and I'll do 4, choose 2. And if I multiply those together, I should get 180. Let's do it. 3, choose 1 times, what did I say, 5, choose 2 times 4, choose 2. And we got 180. Take a look to the bottom right. There it is, what we were expecting. Okay, got a couple more examples. So just to keep it from taking too long, I'm going to just move right along. Actually, what I think I'll do is after I do this next example, I think I'll break this. I'll break off there and do a second video talking about the binomial theorem, because that's kind of a big topic as well. So just to keep things a bit shorter. Consider the placement of the disc in the game. The disc can fall diagonally downward till it hits the bottom. Determine the number of ways the disc can reach the bottom space given the two different placements. Okay, so then again, sort of think of this as Pascal's triangle. Let's start with the one on the right, because that looks a bit more like Pascal's triangle. So it has to go, those black dots here are the pegs. And so it has to bounce down off those pegs and follow different paths. So it could go to this side of the dot below where it starts, or this side. And then from there it could go this. It has one way to get to this space, two ways to get to this space, one way to get to this space, and so on. So it's very Pascal triangle. If we're going to count this as a space here on the left, and I think that the disc could fit in there, so we'll put a 1 there. 4, 6, 4, 1. But then we got a peg right on the side, so we've got 5, 10, 10, 5. So then we got 5, 15, 20, 15, 5. So how many ways? What are we counting? We're counting the number of ways the disc can reach each bottom space given the two different placements. So we've got 5 ways to get 10 points and another 5 ways to get 10 points. We got 15 ways to get 0 and another 15 ways to get 0, and we got 20 ways to get 100. So 10 has 10, well, let's say 5 plus 5 paths. 0 has 15 plus 15 paths. And 100 has 20 paths. And then once we know how many paths there are to get to each of these different spaces, we would be able to come up with probability of getting a particular score. But that's for another time. Let's see how it changes if we place the disc over on the left. So we're starting there on the left. There's one way to get here, and that's the only place it can go. From there it can go here, but there's only one way to get there, and one way to get here. There's 2 ways to get to this path. As we've seen before, it could go this way, or it could go this way, right? 1, 2, 3, 1, 5, 4, 1, 5, 9, 5. Quite a difference. Oh, and there's a 1 here as well. So, to get 10 points, there's 5 paths. To get 0 points, there's 9 plus 1 paths. So 10. And to get 100 points, there's 5 paths. Okay, I'm going to stop the lesson here for now, and I'm going to do a second part for the binomial theorem.